The broadcast is now starting. All attendees are in listen-only mode.
Hi all, I'm Enrique from MestReNova Research, and I would like to welcome you all to our webinar series. Today I'm glad to have once again my colleague Dr. Vadim Zorin, Senior Software Developer, giving another webinar after the one he gave about automatic phase correction last January. In this occasion, Vadim will explain how to use Mnova software for the analysis of multi-component solutions by DOSY and MR processing. For any new ones here, as usual, please write any questions down using the control panel, and Vadim will answer them at the end of his talk. So enough from me. Good afternoon in UK, Vadim. I think we are ready.
Good afternoon, Enrique. Thank you very much for the introduction. Yes, as Enrique mentioned, today I'm going to talk about DOSY processing and tools available in MestReNova to perform DOSY processing. This is a quick outlines of my webinar. I will start with a very short introduction of the DOSY experiment itself. Of course, here at MestReNova, we are specialists in processing data, not experimental aspect of DOSY, so I'm not going to focus about that much, so please don't expect any complicated pulse sequences or complicated mathematics in this section. It's really hand-waving way of introducing DOSY for those who probably not using this before and interested to know a little bit more about this type of experiment. And then I will move to what we understand, what we know is how to process DOSY data in MestReNova, and I will start to showing and explaining what parameters are important for DOSY, where to find them, how to look at them, if needed, how to modify them. Then I will introduce a couple of techniques which are reasonably common for DOSY processing, so-called DOSY transform, which creates 2D representation of DOSY results. We have two built-in techniques for DOSY transformation. The first one is Bayesian DOSY, which is statistically accurate method, which we developed here in MestReNova and introduced it a few years ago. Recently we introduced a new technique which we call peak heights analysis of DOSY, which is a little bit more simple but robust and flexible approach. Many people asked about that, and we decided to introduce it in recent MestReNova releases. I also will be talking about some of the options of both methods, and one of the interesting options I will be talking about is options of dealing with non-uniform gradients. This is a hardware imperfection which can be compensated in the processing, and MestReNova now support this kind of compensation, and I will show how to deal with this kind of problems. And DOSY results is really dependent, the quality of DOSY results really depends on the quality of your pre-processing before you really hit a button which says DOSY transform. What I mean just a general processing operation like baseline correction, phase correction, spectral alignment, reference deconvolution. I introduce a little bit more specific ones and show what kind of difference this result can make for DOSY processing, for the final DOSY results. Okay, let me start from here. And let me start from just a simple introduction, what DOSY does. DOSY basically measures diffusion by means of NMR. So what is diffusion? As we all know from probably even the high school lessons, molecules move inside our sample, inside our liquid samples, and they can push around a little bit bigger particles, which we can observe like Brownian motion. In simplest case, diffusion can be described by something like Stokes-Einstein equation presented here. This is really a very artificial simple case when we have a spherical molecule in sort of continuous media. It's very easy to understand what's going on in here. If looking at this equation, it's pretty simple. So if you have a higher temperature, of course molecules move faster, and the higher the temperature, the faster the motion, the diffusion of the molecules. So it's directly proportional to the temperature. If you have bigger molecules, then they move slower, so you have a dependence on hydrodynamic radius of the molecule. And of course the viscosity of the media, viscosity of your solution is also play a role, and the higher the viscosity, the slower the motion of the molecule. So basically that's what this equation tells us. One of the important, probably obvious, but still important consequence is that if we have a chemical mixture in our solution, we can look how molecules move, and we can discriminate components of this mixture on the basis of their diffusion coefficients. So basically, if we can measure spectra of different compounds with different diffusion coefficients. So diffusion can be this factor which discriminate different components in our mixture. So that's the major idea. So how we can measure diffusion? Of course, we want to measure diffusion by NMR, but let's start from very simple principles. So that's our NMR tube with our samples, and let's imagine that we can somehow, we're not talking yet how, we can label certain molecules within a very thin layer inside our tube. And then we look how these labels distribute itself along the sample. So basically, we start to see diffusion, and if we allow certain time, evolution time, we can see that molecule moves from this layer where they were initially to other part of the samples. And measuring how far they move, we of course can estimate the diffusion. So how we can label molecules in this particular layer? Of course, we are living in an NMR world, so we have to do it in some way by NMR means, and what we can use, of course, is the magnetic field. So we can label them with magnetic field. But the problem is our magnet is, well, basically our magnets are very homogeneous. That means magnetic field is exactly the same along your sample. So basically every point of your sample sits in the same magnetic field. Otherwise you will have a very broad spectrum and useless NMR spectra will come from that magnet. So, but it's good for general NMR, it's not good for measuring diffusion. So to measure diffusion, we use a trick which is called magnetic field gradient. So there is a special coil inside your NMR probe which creates this magnetic field gradient. So basically when we have a current in gradient coil, we can see that magnetic field is slightly different along the vertical axis of the sample. So every point in the sample have a little bit different magnetic field than a point above or point below. So this is a simple graph which shows this dependence. So in this case, we use our magnetic field as the marker. So basically, what is the field at the beginning of the experiment each molecule's experience is our initial condition for our experiment. And then we start running the experiment, and this is a general scheme of DOSY diffusion ordered spectroscopy experiment. So first we apply gradients. So every molecule in solution experiences different magnetic field depending on the initial position. So that's because we have a gradient at the beginning. Then we wait, and molecule starts to diffuse into adjacent area with stronger, weaker magnetic field. And then somehow we measure or counting exactly how many molecules still in the same magnetic field as they were at the beginning of the experiment. Of course, some of them will be probably pretty close. If molecules are big enough, they are not moving that far, so they will probably move in different magnetic field, but not that different. Molecules which are smaller will move in significantly more different magnetic field. And if we can count how many of those molecules sit in approximately the same magnetic field, we know how fast they diffuse, right? So how we can count this? We're using a gradient echo sequence for that. So basically gradient echo can refocus only signals of those molecules which are still in the same magnetic field as they were at the beginning of the experiment. So that's one measurement. So basically what we can see that our signal will slightly decay from the initial signal we can observe in NMR spectrum. And why signal decay? Because some of the molecule moves away and they never refocus it by the gradient echo. And then we repeat this experiment. We can repeat this experiment by increasing delay, letting the molecule move a little bit further away. But what's usually we do, we increase the gradient, and in this way, molecules should move, don't need to move that far away to move in completely different magnetic field. So stronger the gradient, less distance molecule should travel to be in a completely different magnetic field environment. So increasing gradients, you can see that our echo signal will decrease as a function of the gradients. And we repeat this experiment, keeping increasing the gradient strengths. So that's what we see in at the end. So basically that's a graph you can see. So you can see an array of experiment with increased gradient strengths, and you can see that the signal we are obtaining after the echo sequence is slowly decaying down and disappearing. If we take one of that decays, it looks like that. So usually it is an exponential decay, and it could be described by the equation like in this one. So again, looking at this equation, it's pretty simple to understand. D is diffusion coefficient, so the faster molecule moves, the faster the decay. So probably you can see that the water moves faster than caffeine molecule in this, even straightforwardly. You can see it from here. Geomagnetic ratio, obviously. Gradient strength is also the stronger gradient strength, the more attenuation of the signal, the less echo signal you will see. And you need, of course, to include the time, and something happens during the gradient duration, so you need to include both echo delay and gradient duration in here. So it's basically this is coefficients in here, take that into account. Right, so what happens in MestReNova? MestReNova can help you to process this data. And MestReNova automatically load some of these parameters from the experimental data you have got. So where to find it? Let me switch to the MestReNova. Hopefully it's still working. Right, you can find it in so-called array data table. So if you go to the view tables, array data, you should see the table which shows the most important parameters there and here. So this table will look like that only if you have an array of DOSY experiment. If you have, for example, different array like a relaxation delays, some part of this table will be a little bit different. But you can see most of the parameters are loaded here, like geomagnetic ratio, delays, and parameter K. I will discuss this just in a second. And you can see the gradient strength is also in the table. So what are these parameters? Let me go back to my slides. So the parameters are, you can see, gamma is geomagnetic ratio. So that's pretty simple. In this case, this value is for phosphorus. The value you've seen just a few seconds before was for protons. Delta capital is the echo delay. Gradient duration is a small delta. K is conversion factor between the two, between the gradient strength in Gauss per centimeters and gradient strength in native unit. So what is this? It's basically these two columns. So what MestReNova does, it loads the data from vendor software, from the original software, in the units which is used in the original software. The units can be physical units like Gauss per meter or Gauss per centimeter, but in some cases they can be completely arbitrary units like digital to analog converter units, like in this case. So this is value taken from variant data, and this is just an integer numbers which somehow have to be converted into the meaningful units like Gauss per centimeters, and you need a conversion factor. So, and that's exactly what's happening here. So basically you're saying that your G prime is G multiplied by K, and K is the conversion factor used to convert the native units to the Gauss per centimeter, which is used in MestReNova. And then the last column is basically, that's this factor over here, which is an exponential factor in here. Right, so how you can get the values? Well, the simplest and probably most rudimental way is to use data analysis. So you can use data analysis tool and just directly feed your decays. Let me probably quickly show you again, go into the MestReNova and quickly show, if you go to the advanced, you need to have a full version of MestReNova to do that. I don't think it's present in light version or chemist version. And for example, you can select one of the peaks. Let's do it, for example, for the proton peaks. So you can see that I use the integral intensities. I plot in the integral intensities versus X value, and X value is essentially taken from the array data table as a, that's this column. Well, the number of inverted So 234, 234 in here, and y value is the integral intensity of the peaks. And then you can choose one of the equations by clicking this y prime, and most common equation is mono-exponential. You click calculate, and actually you get the values. And looking at the equation, f is your diffusion coefficient. So as simple as that. And you can plot it in here, and actually it will be shown here as well. So you can do it manually. Of course, it's a very simple and rudimental probably approach, but it's a very useful approach very often because you can see directly what you do and how it works in this particular, how it works, and probably you can troubleshoot what kind of problem you can have doing DOSY transform. Okay, let me go back. Yeah, over here. Right, it's probably the simplest way, but you can do something more nice, better looking, and what we are going to do now is basically we're going to discuss a way to transform our decays into some kind of 2D plot where we still have a chemical shift dimension in direct dimension of this 2D plot and diffusion coefficient in indirect dimension. In that way, it's very nice to see because if we take a horizontal slice through this, we can see that this horizontal slice will go through the signals which belongs to one compound. So basically, you can discriminate different compounds in your mixture. For example, in this case, it's 3 components mixture, and you can see caffeine, 2-ethoxyethanol, and water on the different slices of this experiment. So it's very similar to sort of 2D experiment, so it's not really 2D. NMR spectrum, it's rather 2D map. I will explain why such. But it's very nice to look at that, right? So how we can generate that? So we generate it through the operation, we call it DOSY transform. Well, DOSY transform, what it should do, it should take decay and basically find what the exponential constant is in this decay. Sounds simple, however, it's a pretty complicated process. It's more complicated than standard Fourier transformation when you have a sine components or sort of fluctuating components and see how many frequencies you have in these components. And the problem is that it's ill-defined problem, and you can find not a one but several solutions if you don't know how many exponents you have there, if you don't know, if you don't do any a priori approximation or a priori assumption, you probably can end up with several solutions, and it's really a problem with the processing of exponential decay or multi-exponential decay. So what we can do, it's different approaches. Many people develop different methods for that. The simplest approach is basically, in most of the cases, diffusion is a simple case, which needs just a single exponential fitting. So if we say we just have one single exponent, that simplifies quite a bit. So in this, and in many situations, it's absolutely true. But there are some complications, and we have to remember that probably at some point we are going to see them. One of the major complications is overlapping peaks from different compounds. So if you have peaks coming from 2 different compounds and they overlap in the frequency domain, then any area when they overlap, and if we try to extract decay in this particular area, we can see that this decay is not non-exponential. It's sort of a mixture of the decays from component A and component B, which contributes to this overlapping part of the spectrum. So somehow we need to deal with that. The other problem that peaks are not always aligned. So peak a little bit drifting when increasing gradient trends, a lot of interesting things happen in the spectrum, and peak can little move away from its initial position. And that means if you take really a single column, you can see that this single column doesn't go through the top of the decaying peak. So you have to be careful with that. And the standard artifacts like baseline artifacts, phase artifacts, excessive noise, they all complicate DOSY processing. So DOSY processing is pretty involved in mathematical operations. So we have 2 approaches, and the first approaches I'm going to introduce is so-called Bayesian DOSY transform. So how Bayesian DOSY transform works? So essentially, we take, first of all, every column of our pseudo 2D array data set. Yeah, some of them go through noise, some of them go through peaks, and probably from the top of the peaks as well, right? And then what we do, we just try to sort of scan different diffusion coefficients and see how these different diffusion coefficients fit the data. So basically how probable that our decay or not decay or just a straight line function, how probable this function has this particular diffusion coefficient. And this is a part of the Bayesian analysis, and basically what we get at the end, we get a probability to find this diffusion coefficient within this set. And then we plot this value of the probability on 2D plot. So, and essentially the final 2D plot, yeah, like that. And essentially the final 2D plot, if you see a very high probability, they appear as a peaks. Yeah, so that means, yes, it's very probable your data set have this particular diffusion coefficient for this particular column, right? Bayesian approach has several very strong advantages. First of all, it's a really statistically accurate approach. So basically every point of 2D DOSY plot or DOSY spectrum has a certain value. There are no zeros in there. It's all experimental values. All values there are experimental values or processed values. So no unnatural zeros, first of all. Because we, as far as we process every column of arrayed experiment, we also can see that normal line width is present in the frequency domain. We don't do any transformation in the frequency domain. Peaks are positioned correctly and resolved in diffusion dimension. That's a consequence, again, that we do the probability analysis for every point. And one of the interesting consequences is that if we take projection, they quantitatively right. So basically you can see more or less correct spectrum by doing the projection along horizontal axis. So Bayesian transformation is really a statistically accurate technique. Let's probably quickly do an example of that. Let me simplify my picture slightly. So where to find this? You go to advanced. Yes, the first spectrum. Oh, sorry. You go to advanced, and in DOSY transform it's here. So basically it's two methods there. If you choose Bayesian, I'm going to discuss the options in here. And basically what you have to do, just click OK. And that gives you the plot. So basically you can see there are three compounds here, compound 1, compound 2, and what in here. Yeah, so pretty simple. So that's the Bayesian transformation. So what are the options for the Bayesian transformation? Because we scan the diffusion coefficient, we have to specify minimum and maximum of the diffusion coefficient we want to test. So these are these values. Then you have a method-specific options. The first method-specific option is resolution factor. Usual value of resolution factor is 1 or 0.1. So basically it gives you how sharp is your line in diffusion dimension. It's something similar to the line broadening or rather line sharpening function which we use for the spectrum, but in diffusion dimension. But usually something value of 1 or 0.1 gives you a reasonable result, but you can adjust it a little bit to get a little bit sharper or a little bit broader peaks in there. However, if you do sharpening too much, you probably start to miss some of the small peaks. And then number of repetition is basically number of iterations to get the best result out of the data. Again, 0 is absolutely fine in probably almost 100% situation, but if you increase it, you can see that resolution is going up. However, you can start to pick up some artifacts. Right, so Bayesian method is really powerful, statistically accurate, but sometimes it's sometimes too accurate and too correct, and not everyone actually like it. And probably if you have a sort of bad data set, you'll probably see that the plot is also doesn't look very nice. Yeah, so it's basically it's consequence of some of the error estimate, correct error estimate in these cases. And other software packages use a little bit different approach, and so which little bit more, let's say, filtered. So basically you can see only dominant contribution to the DOSY, and many people use it to that. So many people requested this kind of processing, and recently we introduced this as a peak height methods. So this is a classical mono-exponential fitting procedure. So what's going on in this procedure, we basically pick up our peaks, we do the peak picking, and then we see how they decay. We calculate the constant of that, and we create a sort of synthetic artificial plot when we plot the position of the peak on frequency dimension and the found diffusion coefficient in here. And the broadness of the peak represent the error in your mono-exponential fitting. So pretty simple, pretty straightforward way. Can create a little bit nicer pictures by showing just dominant diffusion coefficients in this case, but in most situations it could be the same. Let's just again quickly switch to MestReNova and go to the DOSY transform, switch to the peak height. Again, I will explain new parameters just in a second. Let's do the transformation. So probably just let's flick between two methods. So they pretty much gives the same results, but the peaks looks a little bit more rounded, and mostly because they are synthetic peaks in this case. So you basically you see analysis result rather than just point-by-point analysis in the Bayesian transform. But essentially the results are more or less the same in both situations. So what options can be used? The options for peak height, the specific options are here. The first option is use existing peaks. So as I mentioned, the first step for the peak heights DOSY transformation is the peak picking. And if no peaks are present, algorithm will do automatic peak picking. And actually, if no peaks are present, this field will be grayed out, so you cannot specify it. But if you already did some peak picking and wants to do the analysis only on the existing peaks, you can click here, and basically the final 2D plot will only contain peaks coming from what's already been picked from this particular data set. Autocorrect peak position. So I mentioned already that sometimes peaks can slightly drift from its initial position in the frequency domain. So basically they change a little bit its ppm position. Because we're doing peak picking to build the exponential decay, we actually can track these changes. So if we check these options, algorithm will try to follow the drift of particular peak position and basically extract the intensity straight from the upper points of your peak. So it's compensate minor drift. Of course, you have to be careful if the peak drift is significant, and moreover, if you start to see some overlaps with other peaks, of course, this can only mess up the final analysis rather than really help you. So probably it's one of the things when too much automation can actually hurt you. Overlapped peak analysis. So as I mentioned, overlapped peak is one of the major problems, and there is an automatic tool to help you to deal with the overlapped peaks. So what this tool does, so there are two possible approaches to deal with the automatic peaks. So one of the approaches is trying to use not non-exponential but multi-exponential, 2-exponential or bi-exponential or 3-exponential decays to analyze overlapped regions and try to plot not one position along diffusion axis for a certain point in the frequency axis, but 2 or 3. Yeah, so you can do it in this way. We do it a little bit different. So what we try to do, we try to deconvolve essentially the overlapped regions, try to find the intensities which are not sort of polluted, intensities of the peaks which are not polluted by intensities coming from the neighbors of these peaks, and plot them in this way and do the analysis in this way. So that's what overlapped peak analysis does. It makes analysis a little bit slower, so we use some tricks to improve the performance, so it's not as slow as, for example, you expect from a full deconvolution of all spectra involved in this particular case. So how it works? Well, that's an example. So on the top you can see a mixture. So it's basically 3 or rather 4 components mixture. So you have glucose, water, and 2 forms of dextran. So if you do just a normal Bayesian transform, yeah, you have a little bit messy picture. If you do peak height transform, but not including the peak overlaps, you actually can start to see here's the water, here is the glucose, and something for dextran. And if you actually switch off the overlap peak analysis, then actually you can start to see that its distribution is bigger. For example, these 2 peaks, I don't know if you can see my mouse cursor, hopefully you can. So these 2 peaks at around 5 ppm, they are split between them significantly bigger because it's more correct diffusion coefficients for these 2. And you can see a little bit split in here and a little bit better discrimination. People who probably do this kind of analysis often may argue that multi-exponential, the alternative approach, can make a little bit better result. But one thing of remember that this approach which we use, splitting the peaks, doesn't use any assumptions. And probably this is not really the best example of that because of the very significant peak overlap in this area. But nevertheless, it doesn't use any assumptions. What I mean assumptions, it's like an assumption how many components you have in your mixture. And the other point to say is that actually multi-exponential analysis and deconvolution is sort of complementary. They're not interfering with each other, and both can be used. We don't have multi-exponential, but it's something we probably can introduce one day to our DOSY package as well. Right, so another interesting feature which we have in DOSY package is support for non-uniform gradients. So what are the non-uniform gradients? So as I said in one of the earlier slides, we apply magnetic field gradients to mark our molecules in the solution. And usually we assume that a magnetic field inside our tube is changing linearly as a function of the position, right? So that's the red curve is the ideal curve you should see. However, gradient coil, which creates these changes of the magnetic field, not always perfect. Of course, hardware manufacturer tries to do it perfect, but its real world is never perfect. So you have some deviations from the perfect behavior. So the real gradients could look like that. So as a result of that, our decays, which we see on our DOSY experiments, do not follow anymore a perfect mono-exponential decay, right? But a good thing about that because it is a hardware imperfection, it could be calibrated in specially designed experiments, and knowing the profile of the gradients, which could be done experimentally, measuring experimentally, we can construct what is the real decay function. So it's not going to be exponential, it's going to be a little bit more complicated, which involves so-called non-uniform gradient coefficient in that, but this decay function can be very well described. And if there is an ability to use this decay function to analyze our data, that should improve our final results. I will talk how a little bit later. So at the moment, MestReNova support variant, agile, and DOSY, well, mostly because we know how they store NUG coefficient, where to find them, and how to construct the final function. But basically, the idea is the same for our vendors, and as soon as we start to see many data coming from other vendors using this approach, we can incorporate the support for this approach for this technique as well. So how to use non-uniform gradient? Well, basically it's very simple. As soon as non-uniform gradient calibration is present in your file, so the coefficients are present, you will see an extra box in your DOSY transform window over here with 2 options. The first one is very straightforward. Do you want to correct or not for non-uniform gradients? If you click here, instead of simple mono-exponential fitting, a more complicated fittings will be used, which takes into account non-uniform gradient coefficient. And actually it will support both type of transformation, peak heights and Bayesian. Yeah, so we can use either of them and results will be improved for both of them. And there is another one which is probably less intuitive, but basically the problem is that the average field strength also should be a little bit corrected. So how we do that, it basically we have to correct the coefficient K in array data. You remember it is a coefficient which transform values from native units to the real Gauss per centimeters values of the gradient. And so if gradients are not uniform, these values should be adjusted a little bit. So usual way is basically autocorrect gradient strength should be checked together with correct for non-uniform. So both boxes should be checked. Yeah. So and this way you have a fully automative analysis of your data. Why this box present at all? Well, because in the array data table, user can change the value of coefficient K manually. And then you probably don't want your software to really mess around this average coefficient K. And in this case, you probably want to leave this box unchecked. But it's a very rare situation. I would say both boxes, if you want to use non-uniform gradients, please check both boxes, and that should provide the best possible results. Right, so what the non-uniform gradient compensation does, usually, well, depends how big is the gradient, how non-uniform are the gradient. If they are very uniform, probably not much. But if there is a big deviation, two things can happen. First of all, position can slightly change, as we've seen on this picture. So you have more correct diffusion coefficient values, absolute values. But also you can see that because your fitting function is closer to experimental data, you also can see that the fit has a better error margins, mono error margins. So it's very difficult to see in here, but you have a slight improvement in the width of the peaks. And as I said, non-uniform gradients can be compensated for both Bayesian and peak heights method. Right, so at this point I probably a little bit switch my gear and we'll start to talk how to prepare data for DOSY to get the best results using one of these two methods, Bayesian transform or peak heights. And there are a number of experimental imperfections which affects DOSY transformation quite significantly. One of the major one is the baseline offset. So what baseline offset does, that actually if you look at the particular peak, you can see that the peak does not really decay down to zero because you have a little bit baseline roll or baseline distortion. The final point is never zero. So basically you fit something like a black curve on this picture rather than ideal red curve. And so if you try to still fit it by a normal mono-exponential decay, like decay here with two adjustment coefficient B and F, then actually you have a pretty wrong result for the diffusion coefficient and pretty high error margin, so broad peaks and wrong position in the DOSY experiment. What you can do if you're doing a manual analysis like in data analysis, of course you can probably add another coefficient in here like offset, which describe baseline offset, which should give you a right diffusion coefficient, G in this case. However, it's extra parameter in the fitting, which means it will increase error margin for all these parameters. So you still will get a little bit broader lines in most of the situations. There is a little intertalk between communication between different parameters in this equation. So you probably want to avoid that, and you can by just applying the baseline correction. So baseline correction is pretty important operation to do before, especially if you have a big baseline distortion in your data set. So don't expect good accurate value of diffusion coefficient if your data is not baseline corrected. So, and MestReNova has a plenty of options for the baseline correction. Most of them works quite nicely automatically or in semi-manual way, but it's important to do this before applying DOSY transformation. The other artifact you can see is a phase correction. Yeah, so it's also of course important to phase the first row of the spectrum, but gradients also can slightly change the phase over the course of the diffusion experiment. So basically the phase can drift a little bit from point to point. And in this case, you have two possibilities. You either can correct phase for each spectrum, for each row of DOSY experiment manually, or you can use one of the automatic correction algorithm like region analysis. We discussed it some time ago on the webinar, on the dedicated webinar. You still can find information about this webinar online, I believe. And if you don't do phase correction, what happens? Then your little phase drift contribute to your decay. So it looks like some part of your peak is decaying faster or slower, right? And so probably you can get something like that, a little bit diagonal shape in the Bayesian transform. Yeah, Bayesian transform, because it do the transformation point by point, it gives you a funny shape sometimes. Yeah, so you can see these distortions in here. Peak height, because you do just a single peak analysis, it basically doesn't do that. But if there is a phase error, then it's probably still will be translated into the position error in the final spectrum. So it's still a good idea to do phase correction for both techniques. Yeah. The other problem is that what happened if your spectrum is not aligned properly. So basically, this is the diffusion decay, but I overlapped all spectra on the top of each other, and you can see that during the diffusion decay, peak is slightly moving left and right. And again, if I do Bayesian transform, I can get in a shape which is look like that one. So basically, it's also a little bit of strange, broad, and little bit diagonal shape. There is an operation which we call spectral alignment. So what you can do, you can select the region when you do the spectral alignment, click OK, and basically you have a perfectly aligned lines in there. And if you do the Bayesian transform, again, it's improved the shape. You still have a little bit of this butterfly type shapes. It's probably, we can discuss why it's happening, but it's much better and much narrower bit than in here. So basically it's happening because there is probably little changes in the shape of the peak during the transformation, and maybe noise contribute a little bit. But it's much better than if you're not doing alignment. And this is not a very strong alignment, disalignment. So basically, if you have really bad cases, you probably have much worse data than this one. So, and the alignment tool is available in full version of MestReNova. Resolving overlapping peaks. As I said, peak height method has a built-in technique which is fully automatic. But fully automatic doesn't always means 100% robust. So probably you probably can try to do it manually. So how to do that? Well, you probably want to increase a little bit of resolution with spectrum. How you can do it? It's several methods of that, and different people like different methods. Well, one of the most simple one, and probably which you can be aware about, is Lorentzian to Gaussian line shape transformation. You can simply make your lines look sharper at a certain expense of the higher noise level by applying correct apodization function. MestReNova has a sort of proprietary built-in techniques like resolution booster or synthetic spectra creation after GSD. And you can create synthetic spectra which uniform and sharp lines after GSD much sharper than they were in the original spectrum. So in this way you have much better resolved spectra than an initial one, and you can do DOSY on this spectra. You have to be a little bit careful with the resolution booster. It's not fully quantitative, so it does preserve the diffusion coefficient. So diffusion should work, but you should remember that actually it can change the intensity of the lines in the final 2D DOSY spectrum. And one of the interesting technique is reference deconvolution. We did some changes in this technique recently, so basically I'm going to a little bit focus on this one in one or two slides further. One thing to remember that if you increase resolution, you probably can see that you have to do a spectral alignment as well, because your lines are sharper, you have to be more precise picking the top of this line than for the broader lines. So what reference deconvolution does? So the idea of reference deconvolution is if you have a very bad spectrum with broad line, most likely it is because you probably did a pretty bad trimming Yeah, so this is a specifically very bad case, artificially very bad case. So you not only have a shimming problem, you also have a bit of sidebands. I think it's a mixture of acetone and ethanol. Yeah, so basically the shape, that should be a singlet, and shape is super bad in this particular example. And the main idea that if you have a poor shimming, then your shape of all lines in your spectrum will be affected by this shimming, and all shapes will be the same. So the idea is to take, if you can separate one single line from your spectrum, separate your shape, let's call it reference shape, and try sort of remove this shape from all remaining peaks and try to replace it with the ideal shape. Yeah, for example, Lorentzian or Gaussian. And that's what reference deconvolution does. Mathematically, it does it using FID mathematics. So basically, we take experimental FID, divided it by FID, which we create from this single reference shape. So we create a spectrum which looks like containing just this line, and multiplied by artificial FID of the one single perfect line. And if you apply a reference deconvolution, you have a result like that. So you, the normal typical steps are described here. So you select the singlet, and then basically you specify what line you want to at the end, and then you apply reference deconvolution. Looks very good. One thing to remember, it also comes with certain penalty on the noise. And another thing, you need to have a sort of singlet in your initial data, which I will quickly mention here. There are a number of new functionalities in MestReNova, which we introduced recently to improve reference deconvolution abilities. So one of them is, well, it's more specific for low field, high resolution NMR, which are very popular these days. And what it does is basically you can save your reference shape. So basically the reference shape probably the same. Shimming is approximately the same for all spectra, never perfect, but you can characterize it on sort of standard compound and then apply it to all other compounds. So you can do it with the new algorithm we have for the reference deconvolution. Better support for staggered spectra, for DOSY spectra, for example, which is very important in this particular discussion. So you simply can select a line from the most intensive line from the first spectrum when there is no decay yet, and then this line will be applied to all spectra. Yeah, so that's adjustment. And something else like adjustable satellites, position, so J coupling can be adjusted. Also, there is a problem with the singlet. As I mentioned, you have to have an isolated singlet. But what we do, we can do GSD, and we can actually remove some unnecessary, unneeded peaks from GSD model, for example, impurity peaks, and sort of construct this singlet from a reasonably crowded area. So you can try that. It's not always works, but in some situations it's improved dramatically, and there is also quite sophisticated algorithm which improves signal-to-noise ratio by killing so-called occasional zero crossing artifacts. I'm not going to focus on that one. It's a little bit out of the scope, but basically there are new functionalities for reference deconvolution in the recent MestReNova versions as well. And that's basically it. That's my part. That's what I was going to discuss today. Well, conclusion on your screens. So I believe DOSY is a powerful NMR experiments to study diffusion, and MestReNova provides a good set of tools to do the effective analysis. Most of that is fully automated, so basically you don't need to worry about that. In most of the cases, you just load your data and press DOSY transform to see the DOSY picture. Sometimes, yeah, you have to be careful, because I think if your data is not perfect, you probably can see some imperfection on the spectrum. And I was talking about some way to improve the final results, either by using some of the options available for the DOSY processing, or just use the pre-processing steps, clever pre-processing steps, to prepare your data in a perfect way, so your result looks almost perfect at the end. And that's what I wanted to talk about today. So basically that's the end of my part, and At this point, let's see if we have any questions. Yeah, there are a few.